sequence, by the way, here, because we need this guesstimation of what's going on. All right, yeah.
What? No. The one. Never mind.
So this may actually be a good way to look at intermediate disturbance too. So imagine, so you guys remember intermediate disturbance, that's when you take a system and you shift it to a new system, and you can do that in time or space, right? So you could have a coral and an algae sitting next to each other, and the place between them would be the disturbed site. Or you could take one system and you could kill it off and change it to a new one, and it would go through this intermediate step, and that's what's called intermediate disturbance. And one of the things that we notice in intermediate disturbance is an increase in diversity and some other things. What I think we might be able to argue is that we can see this in this graph, basically. It would look something like this. When you're going through a disturbance starts, and what happens is rare things start taking over, and they ramp up. And you actually run towards maximal entropy. But then when you go into another climax community, you end up with something that looks more like the spiral information, right? Where you have more, you're not doing it as efficiently anymore, right? So you're producing more diversity in a climax community at the cost of energetic efficiency here, right? So this is just to leave you with this idea that we can maybe get to most of the ecological theory behind it. So let's go back. So let's just step back to where we started. So what is going on in these things is there's one force that actually really matters out there, and that's gravity. Okay? And gravity is much like a viral information, except it's a physical version of this stuff. So gravity is what puts things together. It's actually what creates the sun and so forth. That's where you get fusion, right? And you get light, and then photosynthesis going through the system, right? So it's an organizing principle, even though it looks disruptive because we're looking at photons and stuff coming in. The other thing for life on the planet is that gravity is what built the elements. Elements are what gave us fission. Fission is what gives us the distillation of both in terms of the solar system as well as on the planet. That's how we get the chemosynthetic gradients. Things like hydrothermal vents, right? So this is just where you have one redox thing sitting next to another redox thing. This is probably where life started. This is what life that we studied for the most part. So all of this organizing principle only came from this part right here. Good? You guys see that? So it's only really one force that you need to do that. And then what happens is that as soon as you get these guys, and I can show you how we think about this, but I'm not, I did put it in. These guys automatically give you food webs. Right? There's no way you don't get a food web out of it as soon as you start doing any of this. And this feeds, of course, the food web. The first one will be the microbes, and the microbes, of course, are being pulled by the viruses. And what you do is you get things being pulled from this part of it to things being out to the viral information, right? So that you're actually pulling information across that thing. Okay, and those, of course, are the people that have to listen to it. And I was just going to show you this one because there's even more evidence that you might find this stuff. There are these complete conserved things in highly diverse animal systems and in plants. These are exact copies of things that have been maintained through evolution, and we don't have any way for that to have happened. Right? Drift should have given us changes there. So the idea would be that the argument has to be, it's probably working at a cellular level too, which I didn't believe that at first, but there is evidence of it there. Right. Okay. questions? Yes?
Yeah. Well, why don't we just get stuck at phage? Is it because like decay? Physical?
We're feeding it. We've got a whole
Like in that calorimeter.
note here, we're feeding constantly. So right now, you're in this part of the universe where what we're doing is everything from this is feeding that part of it.
To be pulled in that direction means like that needs to be infinitely, that capacity needs to be infinitely large.
Right. But it's not, right? But that's what we're observing still, is that movement, that direction. I think is what we're seeing.
So why don't we get pulled to like a limit where it's, we can't, I would think we couldn't go back past a certain number of phage on the planet to no longer have any food.
Well, we're at a steady state, right? But that's so we're at some steady state where we keep pulling things this direction. They cycle though, right? Because
That's what I'm wondering.
the breakdown products still end up here. So we're still sitting here. Right? That's what's going on right now. And will for the next 8 billion years on the planet or something of that nature. Right? However long the planet lasts. So that's where, or the background of what we're trying to do with the calorimetry right at the moment. Let's see if we can understand this. What I want you guys to get, because it's it's hard to think about, right? You have to think of a long time to understand it, or to actually start to get it intuitively, and of course it's not really completely there, but I think we can test it using these sorts of approaches, and what we really need is to do, this is the isothermal version of it. It would be really nice to do the bomb calorimetry part of it, and have and to do that in real systems, right? So even if all of this is wrong, it actually gives us a background to work against.
So what about the idea that with greater diversity you get increased ecosystem functions or increased?
Right, so that never seems to hold up, right? So it's a great question, right? So why do we not, so we, like everybody always says, the greater the diversity, the more we're going to be up here, right? We should be approaching maximal entropy in the system, right? But if you go and you look, mostly, honestly, this has been done with macroorganisms for the most part, but you don't actually observe that. It's basically half and half what the literature is saying, if you just, the papers that I got through. So it doesn't seem like this hard and fast rule of the system, and I think the people that are finding it are looking really hard for it. So I would propose that actually, that if we do find that climax communities do give you maximum entropy, then it would say this part doesn't exist, right? Then we don't have to worry about this part, and that that's not true. So it's actually a real test. So that's something that is a prediction of this. So it's experimentally, we could maybe do it in well, actually we could do that in a test too, right?
Well, is a climax community generally diverse or not diverse?
Depends, right? So we have lots of climax communities that aren't very diverse. Right? We have lots of climax communities that are extremely diverse. A coral reef and a rainforest are very diverse. A tundra is not. Right? But those are those are true climax communities. And they're never as diverse as a disturbed system, right? As far as we know.
Could you separate it further by calling one, actively an active climax community versus one that's pretty much like in the tundra, that's it, that's all you can see?
Now that is a climax. That's basically, it's the final stage of the ecosystem succession. Right, so there is no real, the climax is a relatively good idea, right? So it seems to really exist. It doesn't mean that there aren't, multiple stages of the climax community. They're approaching that system, and they can be extremely diverse, right? That's what a coral is. A disturbed system, you see more variety in it. Though I have to say, this is what intermediate disturbance is trying to tell you, but I don't know if that's really true, to tell you the truth, because part of it is that you could, perhaps one of the best explanations, at least for a lot of stuff that's been done, is that really what you're seeing is that if you had your rate abundance curve, right? And so imagine we go back to that sort of thing. So you have the rate abundance curve. And these guys, these rare guys, you never observe, right? So you never see them. Okay? And then what you're doing is you're moving to another system. So this is C and this was A out here. And then as we move to another system where we're going to have Z here and A here, right? As we pass through these mixed communities, we're going to notice Z at some point, right? We've never seen it before, never seen it, never seen it, never seen it. And suddenly it comes up here, like somewhere in this part of it. And now it's here, and if we have enough sampling effort, we notice that it's there. Right? So I think that that's probably the best explanation for why we see intermediate disturbance.